So the reason we chose to invest in making a model and do this project is so we can understand some of the harder problems associated with stage 1 re-entry. In particular, we're looking at some of the unsteady aerodynamic problems as well as the steady aerodynamic problems. Hi, I'm Charlie Radovich. I'm staff engineer and lead for the aerodynamics team at Relativity Space. Some of the key advantages of doing a wind tunnel test and making a model, going to a test facility, it gives us a lot of freedom to point the model into a bunch of different angles of attack, a bunch of different roll angles. We can computationally solve things with a bunch of discrete data points. We can make our best guesses that we didn't miss anything. And also we're checking the physics that we actually simulate in a wind tunnel. What is a wind tunnel? What is this type of facility? What does it actually do? In short, it's a controlled test environment. We can subject our model to known and controlled flow conditions. In particular, we care about supersonic flow conditions for this test. So we're talking about Mach numbers. We're going to test somewhere between Mach 2 and Mach 5 and a bunch of points in between there.
Charlie was deeply involved in the wind tunnel testing efforts. It's been over a year for him working and planning this out. So early efforts were just, figuring out what we want to test, what makes sense to test for us here at Relativity. We mapped out and down selected and got down to NASA Langley.
UPWT, that stands for Unitary Plan Wind Tunnel. It's actually made of two sister test sections. One goes from Mach 1.5 to about 3. The purpose was to measure engine loads, both steady and unsteady.
The footprint of the actual engineering that it takes to get the air exactly the way it should be in that test section is incredible. Primarily what we did is we did sweeps of Mach numbers, Reynolds numbers, angles of attacks, and rolls of our model. So we tried to cover an operating space which is representative of the entry conditions we were after testing.
The data that we're using from the wind tunnel measurements not only used to anchor our CFD predictions, but all of this is back to designing the rocket, right? So we wanted to make sure that we're building a vehicle that is going to sustain the predicted forces and moments that it's going to experience during entry.
We got data we needed. We got amazing Schlieren movies and photographs like the one right behind me. At a high level, Schlieren measures density changes in the flow using the refractive index of air.
We have multiple ways of measuring different things. One example of that is we had pressure taps and coolites, both of which measure pressures. One thing we were doing on the fly is sensors in a similar area should give a similar answer. We know how things should behave. If they're not behaving that way, that's a red flag. So basic checks like that and just plotting things up and plotting trends, comparing to CFD and making sure things that are moving in the right direction was really a full-time job and turning the crank as the data kept coming.
This is about as exciting as it gets for the aerodynamics team. This is effectively our flight test. So the results of this test will be used to either confirm or find out what the driving load cases are. We want to make sure this vehicle is going to be reliable and reusable, so we got to make sure we get the design points and the design cases handled that'll make sure that we can bring this back home safely.